So I want to talk today about steam dryness in particular. I've spent 40 years of my life in applied research, and there's nothing better than to get me talking about technology. Because I'll keep going unless Betty Jane shoots me at the end. So, okay. The first point I want to make is saturated steam. 100% saturated dry steam is really a transient condition. What I mean by that is that steam that is dry, has no water, but is in equilibrium with moisture, only exists at a finite point. And if we move away from that point, then the condition of the steam is going to change. So a very, very difficult thing to achieve. And it's the highlights that really the important thing in steam systems beyond steam dryness is consistency and managing a steam system so that you get consistent performance in terms of dryness. It's important, particularly in processing, both CIP and SIP, adherence to EN 285. And so EN 285 is 95%. I know here in the US, you target 97%, which is good practice because of the vagaries and the uncertainty around the manual method that EN 285 describes. And so, as I mentioned earlier, that discipline, that rigor is important. So, how is steam dryness affected? It's affected by a number of things, and they're listed here. So, the actual level of demand, the velocity of the steam, that can change the dryness in a system. Steam trapping effectiveness. Maintaining good steam system quality depends on a number of traps, both from the point of steam generation all the way through the system, through to the sterilizer or through to the process. And if one of those traps starts to fail or is intermittent, you will automatically see that as variation in steam dryness. Steam pipe insulation effectiveness. I sort of recall some experience here. I went to a very major food factory, which remain nameless, and they insulate absolutely everything in the factory and cover it with very nice polished aluminium covering around the installation. Within a couple of weeks, it looks like the surface of the moon because the workers go around and poke it with their fingers. So it means that insulation, performance can vary. Bits can drop off, especially in tech space. Sagging in pipes, uncommon, but also can result in condensate being stored in the sag part of the pipe, and then when that builds up to a certain level, suddenly it will take the condensate through to the end, and you end up with wetter steam. Dead legs, the same reason. Very interesting area is separator performance. There are many different types of separator on the market, and each of them have a particular sweet point. And if the system's operating at that sweet point, all good and all is well. If you're away from that sweet point, then you might end up with wetter steam than you expect. And pressure regulation, whether or not the PRV is operating well, is also important to steam dryness. So really the point I wanted to talk about today is beyond the EN 285, is that monitoring steam dryness is actually a really good system tool. It's a tool to be able you to keep a check on the overall health of your steam system. And we put the inset there of a blood pressure monitor because it's a very similar kind of thing. If you monitor your blood pressure, that will tell you if something's wrong. It won't tell you what's wrong, but it'll tell you something's wrong. And then you've got probably go to the doctor or the hospital to find out actually what's wrong with you. And the same is true, I think, on a steam system with steam dryness. So at one level, it gives you a quality assurance record, which can be very, very important when you're looking back at what may have happened to batches, how your steam system is performing. Also, you can review those trends, and it gives an early heads up that the system is deteriorating a long time before it causes any problems. and it gives you the ability to call the experts in if necessary to actually resolve the problem. So how do we do it? This inset here, you'll see there's a steam dryness sensor. What the steam dryness sensor is effectively a high temperature, high frequency microphone. And what we're doing is we're listening for the sound of the condensate droplets as they impact the microphone. And what we discovered, and the middle inset there, you'll see there's a whole load of data, a lot of different frequencies, a lot of different gain of those frequencies right across the band. And if you do an FFT, a fast Fourier transform of that, you end up with a picture like this. And what's really important is that in certain bands we can see that dryness varying, and so we can actually measure dryness. And unexpectedly, what we found also is we can see the velocity as well. So with a 2-wire sensor, we can pick up both velocity and we can pick up dryness, and that gives us the ability to actually output a dryness signal. So I want to point a few things out here. I want to come off, before I run this video, this is very early research work a few years ago. Dryness sensor is here. This is a sanitary sight glass. And I'd point your attention to that because when I run the video, as this steam becomes wetter, you'll start to see condensate appear. So I'll just run that. Now in a minute you'll see Dr. Mitchell Kane. You don't actually see his face, but he's going to pour some water over the pipe to actually cool the pipe. Now you can see the water he's using is clean, so it's not what you think it is. Right? So, right. If you look at the sight glass, you'll see the condensate there, and you'll see that the dryness now, as the reading has gone down. Take the water away. And the dryness recovers. So that's a dryness sensor in real operation, and some very early research work. We make this sensor in 2 versions at the moment. One is what we call the InLine version, so we can go through a sanitary T. And the other is we've made a longer version which retrofits to a standard test elbow for the pharmaceutical industry. Now the test elbow one raises, I think, a really interesting discussion point between what we call faction or value. So those in the steam world will know that condensate likes to travel down the bottom of a pipe mostly until it either builds up and the steam picks the condensate up, or it gets to a level where it starts to fly with the steam again. So actually in the industry, using a standard test elbow can arise in giving you false dry readings because the actual condensate is bypassing the actual test elbow. So we call that value. If you're really interested in the true dryness, what you can do is put a slight disturbance before the elbow. A disturbance may be just a little raise in the pipeline to actually spin the condensate off into the steam. And then the sensor will give you an absolute real value of dryness. And we call that faction because it's a true faction of how much water is in the saturated steam. Later on in the presentation, I'm going to show you a picture of the test rig that we built in Cheltenham to be able to do all this work. And we had to do something really, which is, I think is the world's first, where we had to build a test line where we could guarantee we can manufacture steam to a known dryness condition. And I'll touch on how we did that. And we had that rig validated, so we know its accuracy. We know that we can use that then to actually make some comparisons. And this chart here is a comparison between the InLine sensor we've developed and the manual method that you're all familiar with. And I've picked out a series of data at 95% dry to actually make the point. So that series of data, you can see that on manual calorimetry, we end up with something like a 2.5% of dryness uncertainty in the data. And that's not untypical, and I think that underpins this practice in the USA of aiming for 97 rather than 95 to be able to guarantee that you actually hit EN285 at 95%. And certainly from my visits around the pharmaceutical industry, you know, I've seen best practice, and to even achieve that means they use the same person every time, they use the same procedure every time, but still within that technique there's that uncertainty. Moving to the InLine sensor, we can get to within 0.1%. We've done that over many years of data, so we know we've got a highly accurate method which goes beyond the manual technique. So this is a picture of our test line in Cheltenham, where we have the Spirax Sarco's Global Technology Centre. It's where my office is based. And you can see on that control panel just how much infrastructure we have in terms of control. And the reason for that is, how do you create steam at a known dryness, at a guaranteed dryness level? So we start with steam, we superheat it to a known value, and then we inject water. And we inject water and make sure the water's mixed. And we then know at a point in that line exactly what the dryness is. And that's what's been underpinning all of this work that I've been explaining today. Now, I mentioned that this is not currently on the marketplace. It's very early stages, and it's actually quite unusual for Spirax to come this early with technology, but we really would like to be able to complete the design and package the design in the way that the industry wants to use it. So really today is about engaging with everybody and understanding, how you might use such a sensor and making sure that we do the engineering. And so, for instance, do you want display of dryness at the head, or do you want to do that remotely in your DCS or your management system? What location for dryness sensors? Earlier today I had a conversation which is really interesting, which was that access to technical space to do the dryness test was a real problem, because after breaking the seal to tech space, they had to revalidate the seal. So having a InLine sensor that was permanently connected would mean that they didn't have to go through that procedure. So thank you very much for listening to me. I've tried to keep it short with respect to Betty Jane. She did warn me. And 5 minutes, thank you. We're at booth 207, and we'd love to engage with you and talk to you more about it and understand how you might use it. And if I left you with one thought, it's to go much beyond EN285 and think about your steam system and critical points in your steam system. And then in the future, we can apply this technology and give you a picture of health of that steam system, which would then be able to give you that quality assurance to actually maintain that for the future. So thank you for listening. And oh, yeah, sure. This one. So you can see there are various dryness peaks here, and the actual velocity peak in terms of gain is much, much greater.